139, Preview Chapter, Section 4. And we're going to look at the application of equations of lines to something called linear modeling. We usually refer to modeling when we're using a mathematical equation to represent a real-world situation. In this section, we'll look at a number of different ways that we might do that, by hand, by calculator, from data tables, and even from just descriptions. So we'll be looking at a number of different examples as we go through. I will run through the calculator skills relatively briefly as I do these, but if you need more calculator instruction, I would refer you to your instructor who might be able to provide you with some extra help or also other videos that would be a little bit more in-depth on those calculator skills. In our first example, we have a data table that gives us the cost, C, of taking H credit hours at a particular college. So for example, to take 3 credit hours, the cost would be $315, and so on. We're going to start by deciding whether or not the data are even linear, because if the points don't lie pretty much in a straight line, there's no point in using the equation of a line for a model. Once we've decided that, we will then try to find a linear function that fits our data. So the first thing I'm going to do is, rather than try and plot all this by hand, which these are pretty big numbers and I can't be that accurate anyway, let's go ahead and use our calculator to plot the data. I begin by entering the data in my calculator, which I do through the Stat menu, right here. And I do want to edit my data. Notice that option number 1, Edit, is already highlighted, and so I just have to push Enter. Now, if you or someone else has used this calculator to put data in before, like mine, you may already have old data in there. So I'm going to go up and highlight the list name, L1, and then just push Clear. And Enter, and that'll clear out the whole list for me. Using my arrow keys, I'll go over and highlight List 2, Clear, and push Enter. And now I've got a blank data table to start with. We'll go ahead and put in the first column, the credit hours. Oops. First of all, sorry, I have to be over in the first column. There we go. First column, the credit hours, 3, Enter, 7, Enter, and so on. And there are my data for credit hours. Moving over to the second column, I'll put in the costs. There we go. All right. The next thing we want to do is put those points on a graph so we can see whether or not they seem to lie on a straight line. And so in order to do that, go over to y equals. And if you do have equations in there, you'll want to clear them out so that they don't kind of cover up your points that you're going to plot. And then going up here, plot 1, I'm going to hit Enter. That turns it on. Notice that when I come back down, plot 1 appears highlighted up here. And that's how I know that it's active. It's going to plot my points. The next thing I need to do is set my window. So I'll go to my Window button. And notice the window settings I have in there right now are not going to be very good for the data that I want to plot. My first column only went from 3 to 18. I usually like to give myself a little space on either side, so maybe I'm going to go from 0 to 20. That covers all those values of H. I can count from 0 to 20 by ones, and that's pretty reasonable, so I'll leave the scale at 1. Now the Y's are much bigger values. In order to see all of those, maybe I'll go from 0 to 2,000. And again, if you said you wanted to go from 0 to 1,600, that'd be fine. We may not pick exactly the same values, but as long as we can see all of these values within our range, we're fine. Now, I don't want to count by ones to go from 0 to 2,000. That's way too many check marks. Let's count by hundreds instead. All right, my window's set. I've got my plot turned on. I'm ready to graph. So I'll just hit my graph button. And there we go. we can definitely see that those points seem really nicely to lie on a straight line. And so I'm pretty comfortable saying that I can create a linear model for this situation. I'm going to set my calculator aside, but don't erase anything because we'll come back to this. All right, knowing that I can find a linear model, I would like to find my equation in the form y equals mx plus b, the slope-intercept form. I'm going to work in that form with the x's and the y's to start with, and then when I've got my final answer, I'll convert to the variables in this problem. So I'm going to begin by saying, let's pick 2 points. You can pick any 2 points you want because they all looked pretty good on the graph. So just for convenience, I'm going to go ahead and pick the first 2. 3, 315, and 7, 655. All right, in order to find the equation of a line, I need to find a slope and find a y-intercept. So find m, find b. To get the slope, I'm going to use my slope formula, y2 minus y1 over x2 minus x1. So 655 minus 315 and 7 minus 3. I'll get out of my graph for the moment. I can always go back. I've got 340 divided by the 4 on the bottom is 85. All right, finding b. I'll go to my slope-intercept form, y equals mx plus b. And we already have a value for m right here. It doesn't matter which point I use. Maybe I'll just pick the smaller numbers. Let's plug in the x and the y from the first point. Oops. So y is going to be 315. The m we just calculated was 85. We'll put the 3 in for x. Plus b. See out 255. And 315 minus the 255 is going to give me 60 for b. So I could write my line. Y equals 85x plus 60. That definitely is the equation of a line that should model that data pretty well. In fact, we can check that if we go back to the calculator. I had my graph, if I just hit the graph button again, that shows the data points. And if I now go to my y equals, and I put in my equation, 85x plus 60, and hit my graph button, I can see that my line does indeed go right through my points, so I've done a good job of finding the equation. The last thing I want to do is if I'm going to write my equation using the original variables rather than the variables x and y, which are kind of generic variables, I would like to rewrite my equation using h and c. H, the inputs, are where I have the x's, and c, or the outputs, are where I have the y's. So the equation that I really want here is instead of y, I'm going to put c equals 85, and instead of x, I'm going to put in h plus 60. One last thing. This problem specified that they wanted the answer written using function notation. And so I'm going to say, well, in this case, C is the dependent variable. That's a function of H, the independent variable, which is 85H plus 60. So there might be my final answer written in function notation. All right, well, let's think a little bit more about this equation and what it tells us about this particular situation. Again, H was the number of credit hours a student is taking, and C represented the cost of taking those credit hours. So let's think for a minute about the slope that we found, the M equals 85, and what it means in terms of this situation. In order to do that, I'd like to go back up and just notice that we were mentioning before that in a linear model, the slope always tells us the rate of change of the function. So in this case, our slope of 85 tells us how the cost, C, is changing with respect to the credit hours. The cost is increasing by $85 for each credit hour the student takes. And instead of saying for each, I could say for each or per credit hour, either way. One of the things I would like you to get used to is always giving me a very specific and complete answer when I ask for the meaning of slope. I don't want to just have you say with a slope of 85, it goes up by 85. I want to know what goes up, the cost. I also need to know how often, for each credit hour in this case. So a complete answer is going to use the situation. We're talking about cost and credit hours. And it's going to tell me how much it increases by. The cost increases by 85 for each credit hour. The other part of this problem was to talk about the C-intercept. Notice that's like asking about the Y-intercept. C was our Y variable. And again, explain what it means being specific. Our Y-intercept does tell us about the starting point, the value of the function when the independent variable is 0. So in this case, our B value, if I look at our equation, is the 60 right here. That would be our starting point when the independent variable, the H, is 0. So we could say for 0 credit hours, the cost is going to be the $60. Now that might seem like sort of a strange statement. Why would you have to pay to take no credit hours? And of course, no one would pay if they're not really going to take any classes. But you all know that you probably pay some sort of a registration fee before you ever actually get billed for your very first credit hour. So if you're going to register, in this particular case, that $60 is kind of that overhead cost or registration fee. All right, let's take a look at another example, kind of similar to this. Accountants for large corporations keep track of the value of company equipment for tax purposes. A common method for doing that is called straight-line depreciation. This table gives us the value of a particular piece of equipment at various times. You can see our times are measured in how many years the company has owned the equipment. 2 years, 4 years, 6 years, and so on. And then the value that that equipment has for tax purposes after every 2 years, in this case the table gives us. The first question I'd like to know is, how can you really tell that the data in this case are linear, even without doing a scatter plot on your calculator? Because the t-values in this case went up by the same amount every time I gave you the value every 2 years, we can compare the y-values and notice that they're going down by the same amount, $10,000, every 2 years. When you have a table that shows that kind of consistency, the inputs are spaced evenly, and the outputs also change evenly, we actually know this is linear, even if we didn't graph it on the calculator. I would encourage you to pause for a moment and just for practice enter this data in your calculator. But I'm going to go ahead and say, yeah, I can see it's linear by the pattern plus 2 in the T's and minus 10,000 on the V's. All right, we're going to go ahead and find our linear function working by hand, and then we will take a moment and put it in the calculator and run our regression as well to verify. So I need to find M and find B. I know I can only work with 2 points when I work by hand. So let's go ahead and again, just for convenience, I'm going to choose the first 2. If I worked with 0,60,000 and 250,000, then I can calculate the slope using my regular slope formula, y2 minus y1 over x2 minus x1. 60,000 minus 50,000. Over 0 minus 2. I almost went the wrong way. When I don't write out the points, just again, make sure you're really consistent. In this case, I took the first one minus the second one, so I had to do it in that same order on the bottom. Gives me 10,000 divided by negative 2, or negative 5,000. Now usually I plug back into the equation y equals mx plus b to find b, but actually I can take a shortcut this time because notice we were given the b value. 0 years after purchase, the value was $60,000. So I can actually just kind of steal that and use it for my b value. So the equation of this line y equals negative 5,000x plus 60,000. All right. Again, in the applications, we typically like to go back at the end and say, wait a minute, now let's use the variables that mean something in the context of this problem. And our x's are actually t values here. Our v's are actually the y values. So for my final answer, I want to first of all rewrite this. Instead of y, I'm going to put in v. Negative 5,000. And instead of x, I'm going to put in t. Plus 60,000. And once again, it did specify that I want a linear function. So I'm going to go ahead and use that function notation. And I could write this as, last time I think I used like a f of whatever. This time I'm just going to go ahead and use this variable as my function name. Either way is correct. I'm just showing you 2 alternatives. So instead of renaming it with a new function name, I could just call it v of t. V depends on the independent variable t. All right. The slope and the intercept, we'll talk about the meanings of those. And again, I'm really looking for complete answers in the context of the situation. So the first one is the meaning of the slope function. Or not the slope function, the slope of the function, sorry. Our slope was negative 5,000. What's changing here is the value of the equipment with respect to time. So we would say this is a rate of change. The value is decreasing by $5,000 per year. One common error here that you want to watch out for is as soon as we've gone to a slope, we've gone to a rate of change. It doesn't matter that the original data was shown for every 2 years. The slope now is doing this per year or for every 1 year. That's actually what happened when we divided out the 2 here in the slope. That created a per year rate of change rather than an every 2 year. So when you interpret your slopes, it's always going to be per unit rate of change, not per 2 years or 4 years or any other spacing that might appear in your data table. All right, in the last part of this problem, we'd like a sentence explaining the meaning of the v-intercept of the function, again being very specific to this context. The v-intercept plays the same role as the y-intercept, so that's that 60,000. And again, the y-intercept is the starting value. Even in the table, we can see it's what happens at time 0. So basically, after 0 years, or right at the time of purchase, the equipment was worth $60,000. And I do want you to practice really that. This is something that's very important because it's going to come up over and over as we do modeling this semester. Really practice when you make those statements, writing a nice English sentence that says very specifically what you mean. Your readers should be able to understand the sentence, even if they've never seen the data table or never seen the equation. All right, we have a few more questions about this particular example. On the next page, we're asked to find the t-intercept of the function we found and explain what it means. In general, when you're asked to find intercepts, you can always find an intercept by setting the opposite variable equal to 0. So in this case, our variables are t and v. If I want to find the t-intercept, that means I set the v variable equal to 0. So my equation is going to become 0 equals negative 5,000t plus 60,000. And I can solve that for t. 5,000t would be 60,000. And if I divide both sides by the 5,000, t turns out to be 12. All right, as far as explaining what it means, in the context of this problem, the t values are how many years since the equipment was purchased. So that would be 12 years since purchase. And v is the value. So at that time, the value is 0. So the equipment has value of nothing, $0, after 12 years. In part D, using our function notation, we're asked to find v of 5 and explain its meaning. So v of 5, we're plugging 5 in for the t value. Would be negative 5,000 times 5 plus 60,000. And that's just a calculator problem. Gives me 35,000. Once again, interpreting in context, t equals 5 would give me 5 years after purchase. The value is $35,000. All right, and one last question about this particular example. I would like to find t when v of t is equal to 8,000 and explain what that means in the context of the situation. So this time I know the v value is 8,000. That goes on the left-hand side. And I set that equal to my negative 5,000t plus 60,000. Notice I don't know t. I can't plug 8,000 in for t. It's the v of t that is the 8,000. We'll go ahead and solve this as well. I'm going to start by subtracting off the 8,000. And so I've got 5,000t, if I bring it over, is equal to 52,000. And dividing out the 5,000 again, let's see, just double check that on my calculator. I get 10.4. So in this case, t again, time after purchase, is 10.4 years. And the v, the value, is $8,000. So my equipment is worth $8,000 after 10.4 years. All right, we're going to go ahead and stop there for right now. We'll continue with this section in the next video.